Please don't.
Okay, so we have our second talk of the morning. Oishee Banerjee is going to talk to us about orbit spaces and stories.
Yeah. Thank you to the organizers, of course, for inviting me here. And thank you for not objecting to the changing the title of my talk in the last moment. So two big thanks. Okay. So I was thinking about how to approach this, and I decided that being the kind of moduli space that is very interdisciplinary in nature, I would talk less about what I or any particular person did about that, and sort of relate it to, in the spirit of this workshop, relate it to, first of all, configuration spaces, because it's the hero of the story, it seems. And second of all, another important moduli space which made an appearance in my friend and fellow speaker's talk, MG. So I'm going to relate whatever the hell this moduli space is to two potentially favorite moduli spaces. Okay. So on that note, I'm going to just structure out some parts of my talk here so that I don't lose track. So yeah, first is going to be Hurwitz spaces. Why should we care about it? And this is going to involve sort of two perspectives. One is called the branched covering, let's say, point of view, and the other is, well, it goes by several names, but let me call it linear systems point of view. Depending on what kind of questions you want to answer, one or both can be useful. I should maybe highlight this fact that nowadays, unlike what many people expected, say, 20 years ago, this has been sort of really impactful than, say, this, which is, as interesting it is, currently less impactful. So like, you know when to tune out, just. Okay. So I haven't defined this guy. I'm going to define what a branched covering is. I'm going to define what a linear system point of view is. I am not going to assume any background about Hurwitz spaces at all. I'm going to draw pictures, which is going to annoy a lot of people here in the sense that I am going to draw disks as lines. The complex will be like a line. And I have a good reason for that, because I want you to think of a disk like, instead of taking a top point of view, you're seeing it like this, okay? So like, think of it still as a disk. Okay, so there will be disks, there will be branched coverings of those. And after completing these two, I am gonna talk about what, okay, I'm going to be a bit cryptic about that, but I'm going to say ramification, stratification, dictionary. So we will learn more about the dictionary and what each of these words mean there. Okay, so, and if after all these story there is time, I am going to mention a theorem that I proved at some point. And if there is still time, and I'm really doubtful about that, I will say a few words about the proof, but that's just like the last 5 minutes. Let's not worry about that. Okay. Can everyone see all the way up to this point? Okay. So, all my spaces will be Riemann surfaces. I might sometimes say words like smooth projective curves, and they should be interpreted as Riemann surfaces. For the more algebraically inclined person, you might say, oh, wait, what the base field is, we won't talk about that at all. Okay. And so whatever word I use, take it to be your favorite surface. The other thing is I might often interchangeably write this guy and this guy. Even if I write this, think of this. Unless you have some favorite. Yeah, feel free. Yeah. And even if I write this, feel free to think of this with its as a Riemann surface. Okay, so that's a teeny tiny notation bit. Okay, so now comes one of my first definitions, or rather the first chapter of the story, the linear system point of view. So to talk about the linear system point of view, I have to talk about what a linear system is to begin with. And hopefully something that I'm going to say here will reduce like 5 minutes from Alexei's talk, because I'm going to define sections of line bundle and how that gives a map. Okay, so the C is your favorite Riemann surface. This is not the complex numbers. Okay, so compact. I should have. It's not like, I mean, we will later on drop the compactness condition at some point, but for now it's going to be compact. So even if I forget the word compact, put it in. Okay, and L is a holomorphic line bundle. On C. Okay, in that case, well, if so you can ask the question whether it has global sections or not at all. Let's assume that L is what is called a high enough, it has a high enough degree so that there are like global sections which are sort of higher genus replicants of polynomial functions in a sense. So suppose, okay, the global sections form a vector space. And I'm going to write it as gamma CL. Okay? And it has, let's assume that it has sections, so like non-empty, or at least of dimension 2. Complex dimension 2. And if I have, so let S1 and S2 be 2 elements here now. Okay? If they share no common zeros, then we'll say that it's giving us a map from, yeah, okay. Then it induces a map and I'm pointedly writing it just map, but you can take it to be holomorphic map, sure. So it induces a map from C to P1. Okay? So just as a quick example of what this kind of thing might look like, let's take C to be a genus 0 Riemann surface, our favorite S2. And if I take what the degree D line bundle on it, then essentially these global sections end up being like, so example, and this sort of genus 0 example is what I am going to mostly talk about all the way up until here. Okay, so example, when genus of C is 0, the vector space of global sections, okay, gamma P1 of, I am writing something here, and if you don't know the notation, don't worry about it. This is just degree, let me call it just degree D, line bundle, the degree D on P1. Essentially what this guy is you can think of it as the vector space of, like, is this the notation for vector space? I mean, C-span of homogeneous degree D polynomial of x to the I, y to the j, where I plus j equals D. So your elements are of the form A0 x to the D plus A1 x to the D minus 1, y to the x to the D minus 1 y, and so on, right? Okay, and when you have two such homogeneous degree D polynomials, you can literally write a map from that, literally gives you a map from P1 to P1 of degree D. You have a point or something? Okay. Okay, so if you have such, like, say, F and G, two homogeneous degree D polynomials, you can take the ratio of that, so to speak, and that gives you a map from P1 to P1 of degree D. Okay? And why do I care about that? Because I care about these maps. Oh, I should have, so, okay, nobody's paying attention maybe. They might have common 0. I didn't rule that out. Okay, so F and G, provided F and G don't have common zeros. Right? Okay, so far so good. It is less about, so whenever I am thinking of sections, I think it's a good idea to think about them as, like, in terms of like polynomials near a point, and because locally it sort of is, and sharing common zeros can be almost sort of phrased as whether around a certain point the polynomial presentation you have has common zeros or not. Okay, any questions so far? Suggestions, comments? Anyone wants me to change any notation? Okay. So that's basically the linear system perspective. I am not technically giving the definition of a linear system, but the word linear appearing here is because you are taking sections of line bundles. So like line bundle, sections, linear. Okay. So that's the linear system point of view. And classical algebraic geometers from as old as, I mean, I don't even know whether they can be called classical algebraic geometers, but like 1870s was Klebsch studying some of these spaces. And well, it makes sense, because if you want to study a particular space, you study the functions on it. And so, sort of for Riemann surfaces, or if you want to rephrase things in terms of like any base fields and smooth projective curves on it, those function spaces are essentially moduli space of maps from your curve or the Riemann surface to P1, provided, again, no common zeros are there. Good? Okay, so that's the linear system perspective of having maps. The other perspective, which is the branched covering point of view, and sort of the more, so if you zoned out during this, maybe come back here. Okay, so instead of having a Riemann surfaces and taking holomorphic maps to S2, we will remove the Riemann surface. We won't even think of a Riemann surface to begin with. We'll just take S2. we will impose some group theoretic data, and then we will construct the Riemann surface as a branched cover. Okay? So it's sort of like here the Riemann surface comes first, maps comes later, and now I have maps first and Riemann surface later. That sort of thing. Okay, so what do I have? This typically involves like, so this is your, I assume that this is your S2. And take a, okay, this is a, okay, I want colors. Okay, so that's my base point. And let's say there are like B points, and there's a reason I'm saying B. It will be clear. So like take P1, P2, dot, dot, all the way up to PB here. So these are like marked points on the Riemann, on the sphere. Oh, I should write that this is a sphere to begin with, right? Okay, and now you consider loops around these points. And of course, these are, I mean, I'm drawing this relatively nicely, but they can be, of course, really squiggly loops. Right? And what you do is you think of, you construct a cover of this punctured sphere, and by cover, I mean an honest-to-God topological cover, and then you sort of put local plumbing fixtures is the word that I really like, thanks to Joe Harris. Local plumbing fixtures, which is essentially saying that you take a map from pi1, p1 minus some bunch of points, p1 to pb, and let me call these loops gamma 1 all the way up to gamma b. And then there's this base point, which I'm going to just write it as a star, right? Okay, and you take, well, you can take any group whatsoever, but let's take the symmetric group over n letters. Okay, and you take these loops, and you map them to, well, one might want to map them to transpositions. It's not necessary. Some conditions has to be satisfied, but let's take transpositions for now. Tau I, where these taus are transpositions. And so the local plumbing fixture is essentially saying that at these points, PIs, when you try to construct the cover, they look like Z mapping to Z square. Yeah, so that's the, you fit in disks by this gluing data. And these transpositions describe the monodromy around it. Okay, so most of the story I have said so far is decently well known. Now the thing is, why do we, how do we rather relate them, A, and B, how do we recognize which point of view is going to become more useful? So here is where I'm going to, any questions? Comments, suggestion? Okay, so here is why I'm going to use these 2 points of views to sort of reflect on the interdisciplinariness of Hurwitz space, which I haven't quite yet defined. And then sort of play around a little bit with this branched covering perspective to get to the point where I can actually talk about the ramification, stratification, dictionary, whatever that is. Oh, okay. So I can go to that board. Can I erase this? Yes. Okay. Okay. So if there are no questions so far, I want to add one thing, which is that you guys might be wondering, I don't know, whether the branched cover we thus construct, I mean, who is saying that that's a Riemann sphere at all? I mean, that's just a topological cover. And to be a Riemann sphere, you have to have some sort of holomorphic structure. And where is that coming from? And yes, I mean, you can say, oh, you pull back the holomorphic structure from the base, and you can do that when you are away from these bad points. But who is to say that you can actually do that even on the bad points? Like, who is to say when you pull back the holomorphic structure via this map, things work nicely, glue nicely? That's the question, right? And even being a classical theorem, it never ceases to amaze me somehow how impressive Riemann existence theorem is, which says that, yes, when you actually construct a Riemann surface this way, it's indeed, well, when you actually construct a branched cover this way, it's indeed a Riemann surface. Not only that, I will make a side note that when you are not over complex numbers and when you can't draw these nice loops, when you're over like a affine line over some algebraically closed field of higher characteristic, even then there are counterparts of the Riemann existence theorem that sort of make this branched cover perspective hold and gives us smooth projective curves over that base field. Okay? So I guess somewhere in this list, I should have written waxing eloquent about Riemann existence theorem, because that's what I just did. So Riemann existence theorem, it is the Riemann existence theorem which describes something as combinatorial as this, and which relates something as combinatorial as this to something which is just about polynomials, essentially. Riemann's existence theorem, or I don't know whether it's called Riemann's, okay, doesn't matter. So that is the bridge between the two perspectives. One is branched covering. One is the linear system point of view. Okay, any questions so far? Okay. So I am going to now present a particular moduli space, and which is one which sort of reflects a small part of the flavor of Hurwitz space altogether, and then sort of generalize that to a general definition of Hurwitz space. Okay, so notice that this sort of a very valid question in this branch covering perspective would be that is there a relation between B and N? Like, can you just choose any B points, and can you just take any symmetric group for like any N and still construct something like this? Is there a vote? Is there other than the people who are like who have really worked on it and they just know? And I know there are people, that's fine. Yes, cool. And that is what is it called? Riemann-Hurwitz formula, is that what it was called? So the B points and this N, they have to have a relation, and it's given by the Riemann-Hurwitz formula. Essentially, you can think of it as like the Euler characteristic of the cover has to be related to the Euler characteristic of the base somehow. And generally, it would have been just N times, like whatever this is like the number, N is like the number of sheets, right? So whatever the number of sheets is, it should have been like that, except then there are these bad points. And the bad points are going to give us some error terms. And these error terms are essentially what is essentially the key trait to stratify the Hurwitz space and try to understand any beat and algebraic data about it, or we beat like cohomology or like topological data on it. So I'm just going to make a, since it seems to be well known, don't forget Riemann Hurwitz. In this situation, and yeah, I have chosen transposition so that it's easier to write down. So I'm kind of cheating. It's going to be what? N times the Euler characteristic of the sphere, so that's minus 2n. This is going to be 2g minus 2, which is the genus of the Riemann surface you end up constructing. And that's going to be plus the number of branch points, which is b. So b is 2g plus 2n minus 2. Absolutely. And not only do I want that, I also want surjection. Yes. Image transitive, surjective, so I've already done that. Even then, the branched curve isn't unique per se. Like you might say, like, is there a 1-1 correspondence even set theoretically for like, okay, yeah, I shouldn't say that. For that sort of Riemann surface and this sort, yeah, so it's not unique. And I'm not going to impose the uniqueness conditions right now. Okay, and this also sort of dictates situations where like you don't have transpositions, but you have like not even necessarily like case cycles inside the symmetric group. You can have like whatever element you want. In the end, you just want the image to be transitive, this guy to be surjective, if you want a connected cover, that is, and I guess we all want that. And just this relation to be satisfied. So the general situation, in the general situation, the Riemann-Hurwitz theorem will say that this B would be like, if you have, say, 3 cycles, for example, this B would account for 2 for each. So like this quantity, here it's, I mean, this quantity is called a ramification index. So the ramification index is 2 in the best case scenario, sort of. And yes, it can be worse. It can be various things. It can be whatever. Z mapping to Z to the n from P1 to P1 is basically ramification index n, right? So one sheet is always accounted for. You have those error terms, and those error terms go into this one. Great. And now what I want to talk about is, given the Riemann-Hurwitz constraint, what if I just, okay, so this sort of branching business seems to be rather local in nature. I mean, the only fact where I use that this is indeed S2 is to say that the product is 1, because whatever loops you have in the end, you can squish it down. That's where I sort of only used S2. If you want just the ramification or branch points picture, which I haven't quite defined technically other than the literal term ramification index. So if you want that sort of a picture, it's okay to sort of restrict locally. With that perspective, I am going to just consider maps to A1, or the complex plane. And instead of taking any Riemann surface whatsoever on top, I will still restrict it to A1 and just see how the ramification points interact. So I am going to define, in light of Riemann's existence theorem, so we are gradually sort of moving towards the ramification stratification dictionary, even though I haven't defined Hurwitz spaces in its full generality. Okay, so Right. If I have, so even when you write polynomials, and these pairs of polynomials representation of maps from P1 to P1, if you just take the domain and the range to be A1, the complex plane, it's like at infinity, it's literally locally z mapping to z to the n. All good? So we know exactly what's happening at infinity, and sort of we shouldn't think of these maps from A1 to A1 that I'm going to talk about as just in terms of polynomials, but rather as maps from P1 to P1 satisfying a certain condition at infinity. So I guess what I'm sort of asking for you is, instead of looking at polynomials as just polynomials, look at them as maps from P1 to P1. Yeah. Mm-hmm. Sorry? This one? Oh, let me write it clearly. Ramification. Yes, so I have given two perspectives, and yes, so I want to, so I've given two perspectives, and now I'm going to define a moduli space and say which of these perspectives give which about the moduli space. So I'm going to, yes. Yes, you want a precise object because it's already 20 minutes on the talk, yes. Where is this leading to? Yes. Yeah, that's a very valid question. Dictionary. Yeah. I was trying to not do that in the beginning. Okay. So, so if Mn is the space of morphisms from A1 to A1, and note that I haven't written it as just polynomials, even though they are, of degree n plus 1, and I take them to be monic, and I go modulo automorphisms of A1, post-composition by automorphisms of A1, so in effect, they vanish at 0. One doesn't really need it, per se. For some rigidity or some uniqueness condition, I kind of put it to make my life easier. And now these maps have exactly this sort of data that you can take any polynomial. And so this is my complex line, right? You're looking at this way instead of that. And this is my complex line, and this is my sort of, the branching data will look sort of like this. So you have sheets meeting at certain points, and these two happen to be like a z going to z square locally. So ramification index 2. And now, of course, not necessarily all maps are like this, and the Riemann Hurwitz is giving you exactly what sort of data is permissible. And a valid question would be, what is the, so like in configuration spaces, we have zeros colliding, and in turn, a polynomial being far from being being different from square free is measured by the number of extra roots it has. Here, the error term, so to speak, is not going to be the number of extra roots it has, but it's just going to be the difference from the normal ramification it has. So in the most general case, like in the most ugliest case, it's going to be something like you have, so this is a polynomial map, so this is C. These sheets are C. This is F. In the general case, you will have something like locally, this is C. Okay, this is C. This is F. Let me call it G. This is E1. And I'm putting numbers EIs, which are like bigger than 2, which has to be bigger than 2. E1, yes. E1 means that it's locally Z mapping to Z to the E1. That's for that case. The ramification index is E1. Actually, I want to use the color chokes to write. So B1, okay, no, I call them P. P1, P2, P3, and that doesn't give the whole picture because there are other branch points maybe somewhere. This is just a part of the complex plane. And this is E1, 1. Let me call this E1, 2. And so you have certain EIJs, is what I'm trying to say. P1, P2, P3, say Pj. And there are like E1j, E2j, and so on, Eij, and so on. And what are these sort of combinatorial data is giving me? These are just like over each branch point, and mind you, branch point is a bad point in the range. There are ramification points, which are bad points in the domain, that carry literally not exactly partition of n. Partitions of n will give me sort of vanishing of whether a polynomial has certain order roots sort of thing. But here, this entirely different partition that's giving me sort of a bipartition, but not completely a bipartition either. That's giving me sort of what sort of ramifications are permissible over a certain branch point. Okay? So this is my ramification stratification dictionary in the sense that if you want these numbers to define a stratum inside this moduli space. Any questions? Yeah, please. Which picture are you talking about? This one or this one? I mean, this one or this one, sorry. Okay, yes. Yes. In one variable. Yes, so each polynomial is being studied as a branched cover. So if you have like f of x equals, say, some pi somewhere, the pre-image is going to be the zeros of that polynomial. And it need not be square free. It will be square free only when these are like not branch points, not the bad points. Yes. Absolutely. For every point of C, I have a new polynomial, and the square freeness is giving me my situation. I'm sorry. This I mean the additive automorphism. So like this is like fixing f of 0 is 0. That's it. Just want to fix that. Yes. Sorry. We have used ramification because I have defined the ramification index, which is that how bad a certain ramification point is. This will be on the right picture as well as the left picture, because this is a ramification point. Any point where you have not Z mapping to Z locally, but Z mapping to a higher power of Z is a bad point. So maybe I should just, to be clear, write bad points, and probably everyone knows what bad points are. Now, bad points in domain is ramification point. Not at all. Okay, that is... Thank you very much for saying that. We are solely in the ramification business right now. The stratification hasn't even started. Okay, the dictionary is not this. The right picture is sort of giving you, so I mean, the ramification business is saying that this is sort of a generic situation, the most common situation, technically the Zariski open dense situation, and the complement is given by such bad polynomials in the sense that you don't have just z mapping to z square, but potentially z mapping to higher powers of z, like even bigger than 2, or you might have two such things stacking upon each other and mapping to. So that would be considered as like, so f of x is some pi, and it has two distinct repeated roots, let's say, something like that. Cool? And now the stratification is kind of just immediately resulting from this, because these guys are what is called, I mean, these are locally closed subspaces of this affine space. And that stratifies in the sense that you can take their closure, so then that's a closed stratification, or you can just say that I want to precisely say there are these many branch points, and with this sort of ramification data, partitions of whatever is allowed, and that's sort of giving you the ramification stratification dictionary. So the stratification dictionary is something that I can't even draw because I can only draw ramification. Okay? The dictionary clear? Yeah. Mm-hmm.
And you have some subsets of it, each corresponding to how many branch points you have and how many, what multiplicity is and how many.
Yes, yes, yes. Not just, sorry? There are quite a few parameters here. The number of branch points, the number of ramification points, and their indices. Yes. What I consider they are not, in this moduli space they are not, but that is not to say that if you want to prove something, they don't need to be ordered. In a sense that if you can, you might think that if you want to prove something about unordered configuration space, and if you want certain information, you might want to go to the ordered business. But in this moduli space, they're not. No. I mean, the branch points cannot be ordered with the ramification points. They are the bad points in domain, bad points in range. So that's like already a division.
So if you take a strata, take the closure,
Mm-hmm. Yes.
how is it related to other strata?
That is given by, which is why I spend all those time with the branch covering point of view, because that is given by something like, let's say, let's take these two. This is suppose sheet 1 and sheet 2. So this is like, this is corresponding to the element 1, 2 in that group, symmetric group, right? And now suppose, let's call this, so this is 1, 2, let's call this 3. Let's call this 3. So these two being mapped like the z mapping to z square is corresponding to the transposition 2, 3. So you're taking, so suppose you take this stratum and you take its closure. What does taking closure entail? It's like you are moving these two bad points, these two branch points, P1, P2. You are moving these two branch points closer together, right? And now everybody can guess probably what sort of ramification you get at that point. 1, 2, 3, right? So that's resulting in, and what one should note is this has ramification index 2, this has ramification index 2. It's not additive. The ramification index is not 4. It's 3, right? And this is another point that I want to emphasize. If you are thinking that, oh, well, we have a stratification which is given by sort of partitions of n, kind of like configuration spaces, it's not really given by partitions of n anymore. Like, just partitioning integers for ramification data is just not enough. Am I making sense? I am saying there isn't a monoid known that makes sense here. Yeah. I can't say there isn't, but yeah. Okay? So like you might want to think with what the discussion was before, that, oh, you're splitting up branch points and then you're putting some ramification data above. So that's like partitions of like splitting n into different integers. So like take the Cartesian product of two of those posets and that should give this thing. It just doesn't. Okay, so from what I described just now, it sort of relates to configuration spaces and then shows the difference. Okay, so how does this help us? This helps us in the following picture. So now wrapping up that, and this dictionary. H and G is going to be my moduli space of degree n. My degree was d at some point, who cares? Degree n maps from C, which is a Riemann surface of genus G, and take any one of those. And you take two sections, S1, S2. Okay, you take a line bundle of degree n. You take two sections, S1, S2. And such that, so L degree n on C, S1, S2 in gamma CL, which I defined sort of before in the linear system perspective, and S1, S2 has no common zeros. Now this guy, unlike that guy, is huge, of course. That one was a harmless affine space. The stratification weren't super nice in the sense that they had like nasty singularities as hypersurfaces or subvarieties of the affine space. But nevertheless, the ambient space was an affine space and life was still hopeful. In this case, life is, I wouldn't say less hopeful, but a lot more interesting. So there is an obvious map here, which is to MG. And you might want to say, oh, what sort of n do we want? And that's kind of dictated by the Riemann-Roch theorem, which says precisely when you will have like uniform dimension of the vector space of global sections in line bundles, right? So if we factor this through what is called the pic NG, like the universal Picard, to MG, right? This is, yes. The Picard group classifies degree and line bundles, yes. Yes. This one is defining, so an element here is C comma L, let's say. So the first map is taking two sections in L that don't share common zeros, but like that's projection to these two factors. And the second map is you forget L.
Wait, want to twist by the zeros of S1, S2?
I'm not sure what you mean. I mean, that is kind of in the definition. I mean, I'm writing this as what's called an incidence relation, let's say. So this is inside pick cross like, oh, yeah. This is the definition of, this is a classical definition of, classical algebraic definition of the Hurwitz space. So you wanted a moduli space, and this is a moduli space to begin with. Yeah. Sorry? Okay, so now, so this is this line of, I mean, this bunch of things is coming from the linear series point of view, this whole chain of things. And when n is bigger than 2, what is it called? the linear point of view translates to, the linear point of view in precise mathematical definition is this. The linear system point of view is this. Yes, yes, yes. What about these guys? P1 is S2. The dictionary is somewhere there. C is S2 minus a point, yes. You take out the infinity, yeah. Okay. Something I should write, something I should clarify? That H and G is the classical algebra geometric Hurwitz space. Now, in certain cases, for example, when you have such nice ramification situation and not these situations, and I mean you literally have 2n plus 2g minus 2 distinct branch points. The preimage of each of them has just one point that has the ramification z mapping to z square. In that situation, you can also get a map of this guy via the branched covering point of view. Actually, no, to get this map, you don't need the branched covering point of view, but to understand this space as a cover of this, you do, which is unordered configuration of 2n plus 2g minus 2 P1. Right? Sorry, H, let me write it this way. H and G simp, and the simplest situation is standing for the simp. So this is sitting inside this guy, and this guy maps to conf Yes, the simp is the simplest situation, which is that one. That picture. That picture, right? Because having branch points is forced, having ramification points is forced. The simplest situation one can get is having index 2 at distinct points and not one over each other stacking up or something like that. That's literally the simplest situation. And in that simplest situation, you get this map. And this has been attacked from yet another point of view, which is, so this is the branched cover point of view, and this can be also studied simply as, well, I wouldn't say this arrow is the branched cover point of view because this is given by that picture literally, but you can sort of study this not from the linear system perspective anymore, because you can afford to study it just as branched covers of P1. That's what I mean. Great. So we had our two finite moduli spaces. We have got connections to them, and we also know what the ramification stratification dictionary sort of is. How does that all of help? How does all of that help? Well, once you have this dictionary, it's going to give you what's left is sort of understanding the geometry of each of those stratum. And if you have an understanding of each of those stratum, you can hope to Well, to use the nerve covering theorem, which people have been using for ages, it sounds like a nice idea, but you need a good cover for that. And this hardly seems like a good cover in the sense that bad ramifications are happening, so the stratum has singularities and all that. So what it means is like you need a nerve covering theorem 2.0. You need an upgraded version of that. I'm stratifying my moduli space. I'm stratifying my moduli space, absolutely. This one or this one, either one is fine. Because again, which is why restricted to C helps, because locally the picture is Z mapping to Z square in the end. So understanding the ramification stratification dictionary in something as simple as in the affine space, as a moduli space here, is going to reflect upon what's happening there. Yes, simply branched ones. Yes, it is the biggest Zariski, biggest in the sense of like, it is the moduli space. It is open. It's Zariski open. Yes. Okay. So the point of so to wrap up these 4 boards, and that doesn't need wrapping up, is that even if you have a genus G Riemann surface and just S2, and you're taking maps between that, essentially what it boils down to is somehow you have to have a good knowledge of the ramification. And the good knowledge of the ramification is given by even in something as simple as maps from C to C, which are given by harmless polynomials. And now you can sort of hope that if you have a strong ramification stratification dictionary, which we do have in this case, and if you can understand the geometry of each of those stratum, you can apply an upgraded version of nerve covering theorem. And I haven't quite said what the upgraded version is, but it has something to do with like not having a good cover and still dealing with it, right? Then you can sort of uplift the idea, because the same ramification stratification dictionary holds just as well in the Hurwitz space above, to understand the cohomology, or at least stably, for H simp NG. That's the moral of the story. Any question? Absolutely, absolutely. So, I mean, yes, I'm trying to understand a Zariski open dense part of this total space. So just like, so if your point is like in HNG, you have this H simp HNG. What do we have here? Well, we have the locus of these guys, and let me call that simp N, simply branched polynomials, let's say. Okay, so that simp is the H simp NG counterpart for the very baby case of when you're just from complex numbers to complex numbers. And this guy is the complement of a bunch of singular hypersurfaces, highly singular hypersurfaces. And so it all boils down to, like, if you want stable cohomology, the computation of the stable cohomology via the ramification stratification dictionary means that so HI simp MN, simp N, sorry, and I will stay in the rational world. FII, yes, you can take positive characteristic fields and you can take QL coefficients and all that. Everything works. So if I want this stably, 1 is the ramification stratification dictionary. Two is whatever resulting stratification you get, understand the geometry of those strata, understand, so essentially in terms of those spaces, it will be understand simp M, simp N geometry. And by geometry, I mean in this particular case of when your ambient spaces are fine and you have like singular hypersurfaces, it turns out that some normalization, like a resolution of singularities of those hypersurfaces, are nice in the sense that they have rational singularities. So that's a geometric situation. The rational singularities picture won't hold too obviously in the H and G simp case, but nevertheless, that's a toy case. And 3, finally, use upgraded nerve theorem. And when I say nerve theorem, I mean this stratification is giving me a nerve. This stratification is not a good cover at all. So hence the upgraded word. And I guess the only thing that remains is for me to, so this is SIMPAN. It involves both these point of views. In the definition, it uses the linear system point of view, the way I defined it. In computation, the configuration spaces do appear, of course, because of the branched covering point of view. What I have not talked about here is that how one gets to this upgraded version of nerve covering theorem, but that will be like explaining yet another 30 pages or something. So, and the reason I have not talked about that is that, as you say, that we are, after all, in an ambient affine space. And having ambient affine space still helps, even though my strata are highly singular. When we are not in the ambient affine space, the singularities sort of still translate to that, but the cohomology, of course, gets more complicated. So that's why the technique matters less, probably. Any questions, suggestions, comments, anything? So when this means, if you want the actual numerical quantities, it's not just simp n that I want, but rather I wanted simp mn. This little m sort of generalizes the simply branched situation by like, oh, what if I allow worse ramification, but still not too bad. That m is like the capping of that. It has some combinatorial formula in terms of partitions of numbers that I'm not going to get into because it's a huge sum. Okay, so when this happens, so if when n is bigger than or equal to 3m, funnily enough, all cohomology vanish all cohomology vanish between 0 and 2m minus 1, except just literally these two, in which case this is q. So I is ranging between these. This is q. This is q to the yet another combinatorial quantity in terms of partitions, because you can't just avoid it because of the ramification stratification dictionary. And everything in between vanishes. And up to the point, I forgot the bound of my own paper, apparently, it seems. Up to, it seems, 3m minus 1. So like everything vanish except the 0 and the 2m minus 1 up to this point. Yes, the simplest ramification forms an open dance is the word I probably used, yes.
Okay. And how do you pass, for example, to a boundary of the strata? You add some ramification with higher powers?
Yes. So the boundary of the strata, like one element in the boundary of the strata is going to be like a polynomial, which, it has to be a polynomial, which is going to look like this, as I said, like, going back to the branch covering perspective, you have a ramification which is given by transpositions here in this picture, right? So one transposition is 1, 2, another is supposed 2, 3, and in the boundary, these branch points are going to collide, and you have a ramification whose cycle is given by 1, 2, 3.
So there are 3.
Yes. And you can have definitely worse. You can have something like these EIs adding up. You can have all sorts of things. Yes. And now the question is, like, if I somehow impose some combinatorial condition like this, is this strata non-empty? Are there actual maps between P1 to P1 that actually has this, if you impose some combinatorial data that the Riemann Hurwitz allow you to do, is the straight and non-empty, and even that is involved. Yeah. I started 4 minutes late, but that's okay. Oh, really? Okay.
So let's thank.
Oh.
And then let's continue asking questions. I think we have already not already went into the asking questions. So I wanted to thank the speaker.
Okay. Can I keep the chalk back then?
Are there more questions? I have a question. Why does your result only reach 3m minus 1?
Yeah, I was hoping that you wouldn't ask that, and you did. Strictly speaking, the actual theorem says everything vanishes and not just up to 3m minus 1. Like when n is bigger than or equal to 3m, or sorry, strictly bigger than 3m, everything vanishes and not just up to 3m minus 1. And I don't remember the proof of that, but I do remember that up to 3m minus 1, the vanishing is dictated by entirely combinatorial restrictions. So this restriction is coming from combinatorics. That restriction is coming from combinatorics. The vanishing of cohomology, which is after 3m minus 1, is coming from the fact that they are like rather nice affine spaces. So just to give you a picture, Z mapping to Z to the n, which is like the highest codimension strata, right? The most degenerate thing. That's just like a point. So those really high codimension things are actually pretty good at being affine or something nice. Any other question? No? Okay, thank you.